student for V4.1.2. So that's the version that we use, Spartan. Once you, okay, let me go back here. So once you open this up, what you're going to see is all the fragments. So you are going to make your molecule using the different fragments. So you have a paper?
Yeah.
So the things that you can do with Spartan are, first is visualization in different modes of the molecule. It can be ball and stick, it can be space filling, it can be just a wire model. So those are the different things. The second thing, can you all see this, is bond length, then bond angle, and then you can see the dihedral angle. Dihedral angle is angle between two planes of a molecule. Bond angle is when you have three atoms, so that's the angle. In a dihedral angle, when you have two atoms here and two other atoms, say, somewhere else in the molecule, are they in the same plane? Are they perpendicular? Are they at 35 degrees? So it gives you the angle between two planes. That's the dihedral angle. You can also calculate the steric energy, which tells you how much strain is within the molecule. Then you can calculate the heat of formation. What does heat of formation tell you?
How much energy it takes to make it, the molecule.
Yeah, so this is not the absolute heat of formation that you get from Spartan, because it's we are not taking very accurate values, because those calculations take very long time. So for relative heat of formation, it is very good. When you take two molecules and when you compare the heat of formation, you know that if heat of formation is lower, the molecule is more stable. So it tells you about the stability of the molecule. So the main parameter that you get for the stability is the heat of formation. So however, the values that you get here for heat of formation are only relative values, not the absolute values. Then you can also view the electrostatic maps. That tells you, the red means it is more electron rich area and the blue means less electron rich. You can calculate the relative charges on the atoms, see which has more negative charge relatively, especially when you're doing different structures. Where is negative charge more? Is it on atom number 1 or atom number 2? You can do that. You can, there are many other things that you can calculate, but we will be doing mostly these calculations that I've listed here, and something else you can see. Electrostatic maps, charges, heat of formation, steric energy. Yeah, okay. So for I mean, as we go along, we will see what are the other things you can calculate from Spartan. So the first thing is constructing a molecule. So you have all the different fragments here. This means it's a sp3 carbon, sp3 nitrogen, okay? And then you have a hydrogen. This is a sp2 carbon, sp carbon, and then you have nitrogen triple bond, double bond. So these are all sp3s here that you have for the, I mean, sp3, sp2, sp, and then you have the oxygens. So you have different fragments. You can also have rings. You have a benzene ring, and you have cyclopentane, hexane, and all those rings. If you want to use the rings directly, you could use that. And here on the top, this is, if you use that, you can just delete the molecule. This one is to make a bond, this one is to break a bond. Here, this is to minimize the molecule. When you draw the molecule, you're not putting perfect bond angles. So what it does is, it'll do a very approximate calculation when you press on the E and find the local well in the potential energy diagram. You know, all these molecules have different conformations, so the energy diagram would look like that for different bond rotations. So when you do that, it will see locally which is the minimum energy for the molecule. And when you press that for a molecule, it will pop up the strain energy in the bottom. Okay, so let's first see how to construct a molecule. So we will take your first assignment here, and okay, so this is your first assignment you're supposed to do. So you can start off with the ring there, because the central part what you have is a benzene ring. Do you all see that? So you can click on the ring and just say, and then bring it here. You have the benzene ring. On the benzene ring, on this side, what is it that it's attached to? What do you see here? What type of a carbon is that?
SP.
SP. So you click on the SP carbon here and attach it there. That carbon is attached to another carbon, which is, what is the carbon?
SP.
It's again a SP. So that is attached to a, what carbon is that now? Number 2. SP2. So click on the SP2 and then click it here. Okay. If you want to rotate a bond, as long as you see this red, if you do this with the left mouse, you are going to rotate the entire molecule. If you can just rotate in the other axis. If you do Control, Alt, this is moving the molecule. Control Shift. If you do Control Shift, you can just move that particular bond where you see the red arrow. All right. Now, if you do not put anything on these valencies, the program assumes it is hydrogen. So you don't have to put all your hydrogens. It automatically takes it. So the only thing that you need to put here is a oxygen. So this is a double bonded oxygen. So click on the double bonded oxygen and do that. Okay, clear? So you have here, for most purposes we use the organic. You also have inorganic. If you want to do anything with proteins or biomolecules, you have those here, peptides and nucleotides. Now on the other side, you have this carbon is attached to what type of a carbon? You see that? SP, this one. 10, what is 10? SP2. So you do that. Okay. Now you see the way it's drawn, it doesn't make a difference, but just for convenience, the double bond is not facing that way, but facing the other way, the way it's shown. So you shift, control, and move. So you can move the double bond in somewhere in that position. Okay. And now to that you have carbon number 11, which is also a SP2. And then on this side, you see it is attached to a nitrogen, which is also a SP2. So you click on the nitrogen and do that. That's nitrogen, which is SP2. Now here, this one is a carbon there, number 13. Do you all see number 13? Is a carbon which is SP2. So attach the carbon there. Now on that carbon, this bond is attached to a nitrogen, that is, what is N14? What's the hybridization there? 3 single bonds. So if nitrogen has 3 single bonds, then it is SP3.
Oh, sorry.
Okay.
If it is a double bond, it is SP2. If it is a triple bond, it is SP. So you click on this nitrogen and do it. Clear? So this is the molecule you have constructed. However, the angles and all that may not be at the minimum energy level, and therefore you need to first click on this. So when you do that, it will rotate itself a little bit, so to bring it to the minimum energy conformation. And what you see here, this energy negative 45.9 kilojoules is your strain energy. Okay? Now this molecule, you can view it, this is just a ball and stick model. You can view different ways. The model, you can see ball and wire, this is how it looks in ball and wire, or you can see ball and spoke, that was the original one, or to get a more accurate view of the how much space that actual atom occupies. Yeah, you can leave, you can ask from someone. You can do the space filling model. So this kind of tells you this is taking, the electrons are taking so much area in space. This is the more correct view of the molecule. Although it's difficult for you to see this, all the atoms, but this is in real time, the density, this is what the molecule takes up, the space, okay?
So,
Now,
so is this not more for helping us as a visual aid? Because some of the things anyway that you listed off are things that we're supposed to, they're skills that we're supposed to know how to do just from a description of the molecule. You know what I mean? Like bond angle and stuff, we're supposed to be able to figure that out ourselves.
well,
So-
you can figure it out, but not very accurately. You say 120, right, for a
Right.
trigonal planar, but many times it's not going to be exactly 120 because there are groups, some groups are bulky, some are not bulky, so it gives you the exact bond angle here. And when you say tetrahedral carbon, it's not always 109. There is going to be deviation from that. So here you get the exact
Mhm.
angle.
So it's meant really, I mean, obviously it's a skill to be able to use these sorts of programs anyway, but I was just wondering in the context of this class, this is just really to, we'll never, I'm trying to keep separate the kind of stuff I need to memorize how to do without a computer versus the stuff that I can rely on the computer to do for me.
This gives you the exact bond length, bond angles. It tells you also about whether there's resonance or not, because when you take, I will show you how you know there is resonance. Tells you what area it occupies, the molecule. It also gives you which is the electron rich area, electron deficient area in the molecule. So you get all those details here. All right. So, however, what we have done here by clicking the energy is a very crude minimization. When you want to get the exact bond length, bond angles, you want to do further calculations to make it really hit the lowest potential energy possible. So for that, you need to go to setup, calculations. In that, we need the equilibrium geometry. That means the most optimal geometry for the molecule. And there are different levels of calculations that you can do with Spartan. You have molecular mechanics, a semi-empirical, Hartree-Fock, and then B3LYP. This usually we do for biomolecules, these two. Hartree-Fock is the most accurate, but also takes the maximum time. So if you want really very, very accurate ones, we do the Hartree-Fock. But for our purposes, the semi-empirical is good enough. It's a good balance between accuracy and time. Okay, if you want very, very accurate, you go to the Hartree-Fock, but we really don't need for many of the molecules, we just do the semi-empirical. So what you need in the setup calculations is equilibrium geometry and semi-empirical. This entire molecule has no charge, and therefore you will say total charge is neutral. There are no unpaired electrons. But if you take a molecule which has a charge, -1, that is an ion, polyatomic ion, or any molecule with a charge, then you have to specify whether it's a -1 charge or a +1 charge. You have to go up, it'll tell you cation or it'll dication, or you go down, it'll tell you anion or dianion. Clear? Do you understand that? So here we go back to neutral. If you want to calculate the charges and bond order, you can click that. So it takes a longer time. And then you say, okay. If you want to see how the density map looks like, you again go to setup, surfaces. In surfaces, you say add, and under density, you go to potential. You have to remember this. So you go to setup, surfaces. You may want to take a screenshot of this. It is in surfaces. And density and potential. Okay? And then say okay. And so it is already here. You move the screen out of the way. And then you go back to setup and submit. It'll ask you where to store the file. You can create a directory or just say Spartan 1. There should be a Spartan folder. This is safe. You don't have permission. Oh, okay, just say wherever it can. Okay, so it says it has started. The calculations have started. Say okay. Click on okay, otherwise it will not start the calculations. So now it goes into the calculation modes. You see here, as soon as you opened Spartan, it had the right screen, which was the build mode. And now it goes into the calculation mode or the view mode. So it has completed. Say okay. So this is a toggle between, this is the view mode and that's the build mode. You see the thing here? So this is the view mode and that's the build mode. So now you have the view mode. So now it has minimized this, and this is the optimum geometry for the molecule, and you can calculate the bond distances. So you click on this here, let's make a bond here, this one, the question mark you see. So that gives you the distance. Or you can go to geometry and measure distance, either way. Either from the menu here or you can go up there. So when you do this, you click on that and click. What is this bond here? It was a carbon-carbon single bond, right? So when you click on that, it tells you the distance is 1.437 Armstrongs. These are all in Armstrongs it gives you, okay? It's not 1.54, although it's a single bond, because this carbon is a sp2 hybridized, and that's a sp hybridized. So although it's a single bond, it's not 1.54 because of the hybridization of the two atoms. Clear? This is a triple bond. So if you click on this, you see it's 1.19. I said it's close to 1.21, right, in the lecture. So you get 1.19. This is a double bond. So you click on this, it tells you 1.34. So that's the double bond. It's longer than the triple bond. Do you remember this? Okay. Now you know benzene, there is resonance. Because of resonance, what should it be? All the bonds should be exactly be the same. So you click on this and see it's, what is it, 1.388.
No, it's due like at the end of
Within the error, okay, if you do the Hartree-Fock, you will get exact, but still 1.40. They're not like a single bond and a double bond. They're all in between a single and a double bond. You click on that, 1.40, 1.8. So very close. So it means that all these bonds are equivalent.
Even if it's not the exact same number.
In the second decimal place, you can expect always, the error due to calculations. All right? So that is always there because you're not doing the Hartree-Fock calculation. So you will have that slight error. Now, if you want the bond angle, you click on this angle. So now this will tell you, you have to click 3 atoms for the bond angle. So you should expect it close to 120, right? So this is 123. It's slightly more than 120, and that's because you have this bulky group here. If you click on benzene, you should again see that it should be 120. You see, it's exactly 120. If you click on these 3, this is, is a SP, so it should be 180, correct? And you see 179.49, which is close to 180. Now, if you click on this, if you want the angle here, this nitrogen is sp2, correct? So let's look at the bond angle. It's 120. Whereas this is a SP. The angle tells you what is the hybridization. So here you work the other way around. Find the angle and then you can decide what the hybridization is. So you click on this, this and that. It tells you it's 115. It's not 109. Remember I told you there would be variation depending on the group. So if you're taking this angle, it's 115. Whereas if you take that angle, it is 112. You also have the lone pair sitting there on top, okay? And then if you take this angle here, it's 112. So there's slight variation. So you can get the bond distance, bond angle, and dihedral angle. If you want to rotate, you see this molecule is pretty much planar. Can you see that? When you view it, you see it's almost planar. So you want to see, is it exactly planar or one end of the molecule is slightly off from the other? So if you click on this, this gives you the dihedral angle. So you click on that and say, okay, I want to see whether these two atoms are exactly in the same plane as my benzene ring. So click on these two and click on any two atoms. They don't have to be consecutive atoms. You get negative 178. Anything that is close to 180 means it is almost planar. Okay. Now even in the benzene ring, you want to see is it perfectly planar. So if you click on this, this, and that, you see it's 179.9, which is 180. So you know that all those four atoms are in the same plane. Now you want to see, okay, whether this end of my molecule is the same as in this end of my molecule, the plane. You get negative 21. So it's not exactly in the same plane. There is slightly, this is this way, and that is not 180 but slight 21 degrees. You see that? So this gives you an idea, is it planar, it is not planar, certain angle, and it's important because if you are going to see how it interacts with another molecule, you need to know whether it's perfectly planar or not. And when you learn about UV visible spectroscopy also, it's important to know whether the molecule is planar or not. Yeah? So these are, so you get the bond distance, you get the bond angle, and you get the dihedral angle from here. When you press this, you got the steric energy. Now you want to know the heat of formation. Suppose you're comparing two molecules, you want to see which is lower in energy, higher in energy. So for that you go to display and properties. When you go to display properties, you get here the charge. No, where is it? Display. I clicked on an atom, that's why. Yeah, I have to unclick all the atoms when I do the display properties. Display properties. So you get, this is why is it doing this? It's still giving me a label.
Yes, you can put a box of filters out in one box, everything else in this one.
1 second.
And you guys can.
I'm going to unclick the surfaces for now. Display properties.
Yes, for right now.
I should get a whole data on this. Let me see why I'm.
Okay. You're going to shoot me. Probably this one.
Oh, display. Okay, display output. Okay, I'm sorry. I just got confused. So when you say display output and you go down, it will give you a lot of data on the coordinates and all that, how many cycles it took to do the minimization, and then it will tell you what's the heat of formation. So in display output you get the heat of formation
For the whole thing.
for the whole molecule. Heat of formation is for the entire molecule always. So that is it's 307.3 kilojoules per mole. And you go further, you don't need it at this point, but it'll also give you what are the values for density, E plot and all that. But at this point, you don't need that data. Now regarding the surface, I told you, you click on display surface, and you want to see how the surface looks like. You click on the density and add density potential. Okay.
What is the purpose of adding the surfaces again?
You can see where is the electron dense area and what is the electron. So when you click on the view mode here, when you do this, you see the red spots. That's where you have the electron rich areas. Now here, when you do this, so basically what you do here is go to display and surfaces, and in this box click on the density. So you are able to see this. But when you see it like this, when you click on the molecule, you don't know what atom is where. This is all solid, right? So on the right side, you see the solid. So go to a transparent. So now you see, oh, here is where your oxygen is, and here is where your nitrogen is. And these are the two most electron-rich areas in the molecule. You have a nitrogen here, but this is not that electron-rich. So this helps you in deciding some reactions, which is the most electron-rich areas in the molecule. Now, if you click on, say, this oxygen here and go to display properties, it tells you the area and the volume, just in case you need those. If you don't need the area volumes, you unclick that and then click on the oxygen and then display out. No, not property. I need display properties. Display properties. It tells you the charge on the oxygen that you have clicked is -0.4. Again, it's relative charge, the electrostatic charge, okay? Whereas if I click on this and I say display properties, it is -0.6. Actually, you have more electron density on that nitrogen. If I click on this nitrogen and say display properties, that's also 0.69, though it is not actually showing up on the thing. So it is more, although the charge is there, it is kind of delocalized there. Okay, so that's what it means. So this is nitrogen 14 that has that charge. So it tells you, gives you some idea. If I click on a carbon and say display properties, I see, you see it's so less. It's just 0.1, whereas those were in the order of 0.4 and 0.6 negative. So it tells you which is the electron-rich area in the molecule. Clear? Mm-hmm. You can also see the molecular orbitals and all that if you want to construct, but at this point, I'm not doing that. You can go to set up surfaces. Here is already there. If you want, you can add HOMO that will tell you that's how the molecular orbitals are, you know, the entire, where the electrons are filling in the molecular orbitals. We haven't really gone into MO theory. Once you go into MO theory, you can see how the molecular orbitals look like, where the electrons are filling, okay? Around which part of the molecule is where the electrons are filling. Okay, you don't need this for now. So those are all the things you can get from Spartan. Get it? Mm-hmm. So what I would recommend is just, if you want to construct another molecule, you will have to first close this file and say discard. And every time you will have to start again. Otherwise it will overlap on the old file. You don't want to do that. So again, go to File, New, and then you get this, construct the fragments, and go from there. Yeah? So how many of you are here? 1, 2, 3, 4, 5, 6, 7. So you can teach the other students when they come in, since you have learned, okay?